everyone, and welcome. So if you're running a Cisco ACI fabric, you already know its real power is in automation. But what happens when that automation starts to go haywire? Today, we're diving deep into a super common and super critical challenge, endpoint instability. We're going to show you how to spot the chaos and, more importantly, how to use ACI's own built-in tools to bring back the peace and keep everything running just the way it should. So here's what we're going to cover. First, we'll start with the fundamentals, how ACI figures out where everything is in the first place. Then we'll get into the messy stuff. What happens when endpoints start moving all over the place? After that, we'll unpack the three main tools ACI gives you to get control, we'll zero in on the best one for the job, and then we'll finish up with some pro tips for keeping your whole system clean and tidy. All right, let's get down to it. Before we can even think about fixing a problem, we've got to understand how the system is supposed to work, right? So let's take a look at the normal, everyday, healthy process of how ACI discovers endpoints. Okay, so this diagram basically shows us the brain of the ACI fabric. You see, each leaf switch over on the left, it keeps its own little local list of the endpoints it can see directly. But the master directory, the real single source of truth for the entire network, is the Council of Oracle Protocol Database, or COOP. This thing is synchronized across all the spine switches, and honestly, it's the secret sauce that makes ACI so scalable. And that brings us to this idea of a proxy lookup, which is just fundamental to how ACI works. See, in an old-school network, if a switch didn't know where something was, what did it do? It would just flood the packet out everywhere, hoping for the best. ACI is way smarter than that. When a packet arrives, the leaf sends it up to a spine, which acts as a proxy. The spine just does a quick check in that master COUP database, finds the exact location, and sends the packet only to the one leaf it needs to go to. No more flooding. It's a cornerstone of ACI's efficiency. So, that's the world in a perfect state. But of course, we all know networks are almost never static, right? So let's dig into what happens when endpoints start moving around in weird, unpredictable ways, and how that beautiful, clean, efficient system can get thrown into complete chaos. This is really the heart of the matter, isn't it? In any data center today, VMs are constantly moving between hosts. I mean, that's the whole point of vMotion. And ACI is totally built to handle that kind of mobility. But when a misconfiguration causes those moves to happen way too fast, or just illogically, the stability of the entire fabric is suddenly at risk. Now, here's how ACI handles a good move, a legitimate one. When EP2 moves from the server on leaf 3 over to the one on leaf 4 immediately tells the central COOP database about the move. COOP then lets leaf 3 know about the change. But check out what leaf 3 does. This is the clever part. Instead of just deleting its old record, it creates a special bounce entry. This thing acts like a little temporary forwarding rule, making sure any traffic that was already on its way to the old spot gets seamlessly redirected to the new one. Pretty cool, huh? And this is where the trouble starts. What we're looking at here is a classic misconfiguration. You've got a server with an active NIC team, but it's plugged into two different leaf switches that are not in a virtual port channel, or VPC. So what does the fabric see? It sees traffic from the exact same VM coming from leaf 1 and leaf 2 almost at the same time. This triggers this frantic back-and-forth update storm in the COOP database. That, my friends, is endpoint flopping, and it can seriously mess with the stability of your entire fabric.
Okay, so we've got a flapping endpoint, and it's threatening to take down our whole fabric. How do we stop it? Well, thankfully, ACI gives us a toolkit with 3 different features designed to deal with this exact scenario.
Let's break down our options. First, you've got endpoint move dampening. This one is scoped to a single bridge domain, a BD, and it kicks in based on the total number of moves. Then you have endpoint loop protection and rogue endpoint control. These are both global settings, and they're focused on a single bad actor, a single misbehaving endpoint. But, as you're about to see, the actions they take are worlds apart. First up, endpoint move dampening. The keyword you have to remember here is aggregate. It's not looking for one specific problem child. It's just watching the total move count inside a bridge domain. If that count goes over the threshold you set, ACI takes a pretty drastic step. It just stops learning any new endpoints in that entire BD. Yeah, it'll stop the flapping, but man, it's a blunt instrument. You could easily impact a bunch of healthy, totally unrelated applications. Next on the list is endpoint loop protection. Now, this is a global setting, and it's definitely more targeted because it's watching for one single endpoint flapping between different ports. But look at the actions it can take. It can disable learning on the BD, which we already know can be a problem, or, and this is the big one, it can just shut down the entire physical port. No, shutting down the port absolutely solves the problem, but it also takes down every other well-behaved VM on that same physical host. It's effective for sure, but the blast radius is just huge. And finally, we get to rogue endpoint control. Just like loop protection, it's a global feature, and it tracks a single badly behaved endpoint. But its action, it's just so much more intelligent. It doesn't bring out a sledgehammer, no. Instead, it uses a scalpel. It surgically quarantines only the offending endpoint. It locks that endpoint's location, it raises a specific fault so you know what's going on, and most importantly, it lets all the other services on that port keep running without a single interruption. So, we've looked at 3 different tools, but they are clearly not all created equal. When it comes to handling endpoint flapping, modern best practices point to one very, very clear winner. This slide says it all, doesn't it? Endpoint loop protection's port disable action is the networking equivalent of using a sledgehammer to hang a picture. I mean, sure, it solves the immediate problem, but you're going to have a lot of collateral damage. Rogue endpoint control, on the other hand, is that scalpel. It just isolates the single problem, fixes the instability in the fabric, and has almost zero impact on your production services. So let's just quickly recap the benefits here. It quarantines only the bad actor. It stabilizes the COOP database by locking the endpoint's location down. It generates a specific fault, telling you exactly which device is causing the headache so you can go fix it fast. And, crucially, it stops one misconfigured VM from taking down an entire server. It's for all these reasons that Rogue Endpoint Control is the feature that is absolutely recommended to enable by default in your fabric. Okay, so now we know how to fight fires when an endpoint goes rogue, but let's shift gears and talk about being proactive. What if we could prevent some of these problems from even starting? We're going to look at 2 really powerful features that help you maintain good endpoint hygiene, basically keeping your fabric's tables clean, secure, and accurate right from the get-go. Let's talk about IP aging. Picture this. A Windows VM boots up, but the DHCP server isn't available just yet. So what does it do? It gives itself one of those temporary 169.254 APIPA addresses. And of course, ACI learns it. A couple minutes later, the DHCP server comes online, the VM gets its real IP address, and everything's great. The problem? Without IP aging, that old, stale, useless APIPA address might just sit in ACI's tables forever. By turning on this policy, the fabric will just periodically send out an ARP for the IPs it has learned. If it doesn't get a reply, it knows the entry is stale and it safely removes it. It's a simple way to keep your tables accurate. And finally, we have Enforce Subnet Check. Think of this like having a bouncer at the door of your network. When you turn this on, ACI becomes a gatekeeper. Before it learns any new endpoint, it asks a simple question. Does this endpoint's source IP address actually belong to a subnet that I know is configured for this bridge domain? If the answer is no, ACI just refuses to learn it. It's a super simple but incredibly powerful way to prevent IP address spoofing and just generally keep junk out of your endpoint tables. So what's the big takeaway here? Managing an ACI fabric isn't a set it and forget it kind of thing. It is an active, ongoing conversation between your servers and your switches. Endpoint flapping is just what happens when that conversation completely breaks down. By using the right tools, the surgical precision of rogue endpoint control, and the proactive hygiene from IP aging and subnet enforcement, you get to become the mediator. You can transform your fabric from something that's just reacting to chaos into something that is truly engineered for resilience, for security, and for the constant change that defines every modern data center.